One of the most common questions I see in the UTV industry is what mirrors actually let you see behind you. A lot of riders out there complain about blind spots. Others say they don't use their mirrors like they would on a normal vehicle. Some end up even switching to rear view camera systems entirely. The interesting thing is that the mirror itself is only part of the equation. And before you can even begin to understand performance, we need to understand what's the environment that the mirror operates in. These comments aren't unusual. In fact, they're some of the most common observations you'll see from riders discussing side mirrors on modern sport UTVs. The interesting thing is that the mirror itself is often only part of the equation. Modern sport UTVs such as the Polaris RZR, Can-Am Maverick X3 and Maverick R, Kawasaki KRX and Teryx H2, and the Honda Talon have become faster, larger, safer, and more capable than ever before. They've also become increasingly complex environments for the driver. Larger roll cages, deeper seating positions, wider chassis platforms, integrated windshields, and occupant protection systems all influence what a driver can see. Every machine creates its own unique visibility challenge. 15 years ago, UTVs were relatively simple. Narrow cages, minimal bodywork, and limited protection meant drivers had a fairly unobstructed view around the machine. Today's sport UTVs are different. There's stronger roll cages, larger A-pillars, reinforced structures, windshields, doors, roofs, intrusion protection, and integrated accessories. All of those improvements make modern machines safer and more capable, but every addition competes for the same space the driver uses to gather information. The result's a visibility problem that many riders mistakenly blame on the mirror itself. In many cases, the mirror isn't creating the blind spot. The machine is. Most riders think mirrors create visibility. They don't. Mirrors transfer information. A-pillar, driver position, windshield, mirrors, sightline. Visibility is the result of an entire system working together. This creates an entire information system for the driver. Every sport UTV contains structural elements that occupy part of the driver's field of view. These obstructions, highlighted in red, reduce the amount of information available to the driver. What remains is the driver's usable viewing corridor. This is the area where the driver can effectively gather information about terrain, obstacles, other vehicles, and trail conditions. Creating visibility is only half the challenge. Once the machine starts moving, preserving that information becomes significantly more difficult. Whether it's a sport UTV or a utility UTV, every off-road vehicle is exposed to vibration, impacts, and dynamic loading. In engineering, we refer to this as information fidelity, the ability of a system to preserve the quality and accuracy of information as conditions change. The question is no longer whether information can be gathered, the question is whether that information can be preserved. Every structure has frequencies where it naturally prefers to vibrate. When energy is introduced into a system, vibration can begin propagating through surrounding structures. When input forces begin matching a structure's natural frequency, movement can become amplified, just like using a swing set. The same principle can occur in mirror systems operating under dynamic off-road conditions. As vibration becomes amplified, information quality begins to degrade. We refer to this loss of information fidelity as the Beehive effect. The mirror may only be moving a small amount, but it's going to be exceptionally difficult for the driver to interpret anything from it. Many mirror systems rely on some variation of a ball and socket joint. The interesting thing about a ball and socket joint is that movement isn't a defect. Movement is the intended purpose. The human shoulder is a ball and socket joint, and it was specifically designed to allow movement across multiple axes. Mirror systems using similar architecture faces the exact same challenge. To keep the mirror in position, these systems rely on friction retention. That friction is created through preload, the clamping force generated when components are tightened together. Initially, static friction, often referred to as stiction, resists movement. But over time, repeated vibration, impacts, adjustments, and environmental exposure can change those friction characteristics. As wear accumulates, the system may require additional preload to maintain the same level of retention. The challenge isn't creating movement, the challenge is controlling it. And controlling movement becomes increasingly difficult when a system relies solely on friction to resist it. Off-road vehicles operate in some of the harshest environments imaginable. A machine can experience freezing temperatures in the morning, triple-digit temperatures in the afternoon, and constant vibration throughout the day. Engineers refer to these repeated temperature changes as thermal cycling. Let's look at an example of thermal cycling. As temperatures change, materials expand and contract.
Let's start by taking a look at the sphere that is designed to just barely fit through this ring, so it's sized just right to make it through the ring. Now we're going to use a blowtorch to heat up the metal sphere and see what happens.
Repeated expansion and contraction can influence the forces acting within a mechanical system. At the same time, every bump, impact, rut, and washboard section introduces dynamic loading. Thermal cycling changes the environment, dynamic loading applies repeated force. Together, they create a demanding operating environment for any friction-retained system. At the same time, force applied farther from a mounting point creates additional leverage. Engineers refer to this leverage effect as the moment arm. As the loads move farther from the mounting structure, the forces acting on the system increase. This raises an important engineering question. Should movement be resisted through friction or mechanically constrained from the start? Up to this point, we've discussed visibility, vibration, harmonics, friction retention, and thermal cycling. All of those concepts ultimately lead to a fundamental engineering question. Should movement be resisted or should movement be mechanically constrained from the beginning? This is the difference between force closure and form closure. Force closure resists movement through friction. Clamping force creates pressure between two surfaces, and that friction is what keeps components in position. Form closure approaches the problem differently. Instead of relying primarily on friction, geometry itself limits or constrains movement. Many mechanical systems combine elements of both. The engineering question is not which approach is right or wrong. The question is where each approach is most effective. In a friction-based retention system, such as a ball and socket design, the same interface is often responsible for both adjustment and load retention. In other words, a single pivot point is expected to support the weight of the mirror, pod lights, mounting brackets, and any additional accessories attached to the assembly. As additional mass is added, the forces acting on that adjustment increase interface. Every pound added farther from the pivot increases the torque acting on the system. The adjustment interface must now resist not only the load itself, but also the leverage created by that load. Over time, that creates a growing demand on the same component responsible for holding the mirror in position. Weight is only part of the equation. Gravity, aerodynamic drag, vibration, and impact loads all act on the vehicle simultaneously. In many systems, all of those forces ultimately converge on a single adjustment and retention interface. The question is no longer whether the interface can hold the load. The question becomes how much preload is required to resist those loads over time. When a system is new, there's typically a substantial margin between the holding force available and the loads being applied. Over time, vibration, wear, thermal cycling, and repeated adjustment can reduce available preload. The applied loads may remain relatively constant, but the holding force available to resist those loads gradually decreases. As that safety margin becomes smaller, the system becomes increasingly sensitive to movement, drift, and loss of adjustment. Eventually, the adjustment interface begins carrying structural loads it was never intended to manage. And those demands aren't standing still. Modern UTVs continue to get faster, while mirror systems are often expected to support larger housings, auxiliary lighting, and additional accessories. The loads increase, the environment becomes more demanding, the safety margin becomes increasingly important. Every mirror system begins at the vehicle interface. The clamp transfers load from the mirror assembly into the roll cage structure and establishes the foundation for the entire load path. Any force acting on the mirror must ultimately travel through this connection. Moving outward, the acorn interface provides rotational indexing and positional adjustment. This geometry allows the mirror to be positioned relative to the driver while maintaining a repeatable mechanical relationship between components. The breakaway assembly serves multiple functions within the system. During an impact event, it allows controlled movement to help protect the mirror and mounting structure. It also separates the accessory load from optical loads. The lower mounting bracket provides a dedicated attachment point for accessories such as pod lights. This allows accessory weight and vibration to be managed independently rather than being carried directly through the mirror housing. As systems become more complex, separating functions can be just as important as strengthening components. Finally, the mirror head itself remains adjustable for final optic placement. This allows the reflected image to be tailored to the driver's seating position, vehicle configuration, and visibility requirements. Each component performs a different task. Some manage structural load, some provide adjustment, some manage impact energy, others control optical information. Good engineering isn't asking one component to do everything. It's assigning the right function to the right mechanism. When a force acts on any mechanical assembly, that force must travel somewhere, starting from an impact on the mirror, traveling through the mirror to the breakaway, through the 360 acorn pivot, to the clamp, into the machine. Engineers refer to this as a load path. Modern sport UTVs have become faster, stronger, and more structurally sophisticated than ever before. As a result, drivers operate within increasingly complex visibility environments. A-pillars, door structures, dashboard geometry, and bodywork all occupy portions of the driver's field of view. What remains is the driver's usable viewing corridor. The same principle applies behind the driver. Rear bodywork, cage structure, rear fender geometry, and vehicle width all influence the amount of information available through a mirror system. Just as forward visibility is affected by vehicle geometry, rearward visibility is affected by the geometry surrounding the reflected image. Optic placement and mirror geometry influence how much of the reflected image is dedicated to the environment versus the vehicle itself. In both examples, a reflected image is available to the driver. However, the amount of useful information contained within that image is not identical. When more of the reflected image is occupied by the vehicle itself, less area remains available for environmental observations. The goal of a mirror system is not simply to create a reflection. The goal is to maximize useful information available to the driver. Visibility corridors, optic placement, vibration control, load management, and mirror geometry all contribute to that objective. Earlier, we discussed the Beehive effect. In that example, vibration caused the reflected image to move independently of the environment, making information increasingly difficult for the driver to interpret. One contributor to that phenomenon can be what's known as floating glass. In a floating glass design, the optic is allowed to move independently of the mirror housing itself. As vibration increases, that independent movement can further degrade information fidelity. However, image movement is not the only factor influencing information quality. Mirror geometry plays an important role as well. A relatively flat optic maintains a more natural representation of size, distance, and spatial relationships. Objects generally appear closer to their true proportions and position within the environment. This can improve depth accuracy and spatial interpretation. One common method of increasing field of view is increasing mirror curvature. As curvature increases, a larger portion of the environment becomes visible within the same mirror. The driver gains additional environmental coverage without increasing mirror size. However, increasing field of view and increasing information quality are not always the same thing. As mirror curvature increases, objects appear smaller and spatial relationships become compressed. The driver gains visibility but may sacrifice depth, accuracy, and distance perception. Just as vibration can degrade information fidelity through image movement, mirror geometry can influence information fidelity through image distortion. In both cases, information remains available to the driver. The question becomes how accurately that information can be interpreted. Engineering a mirror system is ultimately an exercise in balancing field of view, stability, depth accuracy, and information quality. The objective is not to simply see more. The objective is to provide useful information that can be interpreted quickly and accurately. So earlier we discussed information fidelity, Beehive effect, and floating glass. In each case, the challenge is preserving the quality of information delivered to the driver. One approach to the problem is structural optic bonding. Structural optic bonding permanently couples the optic to the surrounding housing structure. Rather than allowing the optic to behave as an independent component, the optic becomes part of a larger structural assembly. This actually reduces the effect of the Beehive effect because it all resonates on one frequency and not a bunch of individual components resonating at different frequencies. The goal isn't simply to make the mirror stronger, it is to reduce the independent optic movement, because every time the optic moves independently of the housing, information fidelity can be affected. So earlier we discussed load path separation. Accessory loads, impact loads, and optical loads do not necessarily need to travel through the same components. Separating those load paths allow each component to focus on its intended function, whether or not you want pod lights here, whether or not you have an impact here, whether or not you need to adjust here. You have 3 separate load paths to accommodate that. At the end of the day, the mirror's primary function is delivering information to the driver.